sake of time, I do have another moderator, but I'm not sure when or if he's coming. But I think for this, everybody's, I'm sure, tired. So the sooner we get started, the better. Is that okay with everyone? Yes? Excellent. I apologize, I don't have any bio. Oh. Maybe. All right. We're going to get started in a minute, but one logistical issue, please, for the presenters. Dr. Alat, you want to show them? She's going to help us. She's going to keep track of time. She's going to show you a 5-minute, and then at 1 minute. And if you get to 0, she's tough. I know her. So watch out, okay? But thank you for your help.
Hi everyone. First of all, the first talk will be for Professor Tili Kiranti from the University of Toledo. Professor Tili Kiranti has a bachelor degree pharmacy from the University of Colombo, Sri Lanka, and has a PhD from the University of Oxford, United Kingdom. Right, we can start now.
Thank you for the introduction, and also I'd like to thank the organizing committee for the excellent arrangements we have been hosting, and also for the hospitality from the day we arrived. We have been treated very well, so we have time. So thank you very much. So the title of my presentation today is Structural Modification of Dedicated Cycling of Largazole. Development of more potent selective HTAC inhibitors. So this is the structure of largazole. Before I talk about largazole, let me very briefly talk about histone deacetylase enzymes. Acetylation and deacetylation of histones can modulate gene expression and also chromatin factor. Because chromatin structure provides the chromatin remodeling, which can modulate gene expression. So this slide shows what happens during histone acetylation and deacetylation. This is a lysine side chain of a histone molecule. This is a lysine side chain, and there are two members of two classes of enzymes that are involved in the acetylation and deacetylation process. Now the HATs or histone acetylase transferases acetylase the side chain of lysine to give the acetylated form, and then the deacetylases deacetylate or remove the acetyl group to give the pre-lysine side chain. So when it is in the pre-amine form, it gets protonated at physiological pH, and it interacts with the negatively charged phosphate of the DNA and form what is called the condensed or closed form of DNA. When you see the acetylated form, there is no such interaction, and therefore you have what is called the more open form of DNA. And when it's in the open form, it's accessible to transcription factors, therefore it is transcriptionally active. And when it's in the closed form, it is not accessible to transcription factors, therefore it is transcriptionally inactive. So that can lead to the inactivation of gene expression, including the repression of tumor suppressor genes, which leads to tumorigenesis and cancer. So that is, so in other words, if you can inhibit this process, if you can inhibit the deacetylation process, then you are having the is the lysine side chain in the acetylated form. In that means this one in the open form. So you can that way re-express the repressed immunosuppressor genes, which can therefore can be a potential way to develop anti-cancer agents. So there are 18 different HDAC isoforms in humans. They belong to 4 different classes, class 1, 2, 2 divided into 2 subclasses 2A and 2B, and class 4 and class 3. And class 1, 2 and 4, they are called zinc-dependent HDAC inhibitors because they have a zinc ion in the active site. Whereas class 3, they depend on NADP, so they are NADP dependent HDACs, and they are also called SIRT. So I'm really going to focus on the zinc-dependent HDAC histone deacetases. Now these histone deacetases are overexpressed in certain types of cancers. For example, HDAC1 is overexpressed in certain prostate cancers. HDAC 1 to 3 are overexpressed in ovarian cancers, and HDAC 1 and 2 are expressed in gastric cancers and so on. In other words, if you can inhibit these HDACs, that may provide a way to, to develop therapeutic agents for treating cancer. So now, in fact, there are already 4 HDAC inhibitors that are in clinical use, approved by the FDA for treatment of different forms of cancer. Odinostat or SAHA approved in 2006, and then this is romidepsin approved in 2009, belinostat approved in 2014, and panopinostat approved in 2015. So within the last decade, 4 HDAC inhibitors have been approved as anti-cancer agents, 2 of them in the last 1 year. So this really underscores the importance of HDAC inhibitors as potential anti-cancer agents. Now, this is chilamide. This is approved in China for the treatment of pancreatic cancer, but not in USA, but is in clinical trials in USA. And in fact, there are many other HDAC inhibitors which are in different stages of clinical trials. And one of the problems with these inhibitors is that most of them are pan inhibitors. That means they are not selective for any particular isoform. They inhibit all different isoforms, therefore they have a narrow therapeutic window and therefore toxic side effect, except for romidepsin, which is more class 1 selective. So what is really required is inhibitors which are more isoform selective. So that's what we have been trying to do with largazole. Now before that, I want to very briefly talk about the pharmacophore HDAC inhibitors. Consists of 3 essential parts: a zinc binding group, because these enzymes have a zinc in the active site, so this is a zinc binding group. Then there's a cap group, which is more hydrophobic. It binds to a hydrophobic rim of the at the entrance to the active site. And there's a linker group which links the 2 domains, and it occupies a narrow channel in the enzyme. So, and now this the area surrounding the zinc binding group, the amino acids are highly conserved, whereas in this area the amino acids are less conserved. So therefore, the general thinking is that you can get isoform selectivity by changing this part of the molecule. So that's what we have been trying to do with largazole. I want to now talk about largazole. This is a marine natural product isolated from cyanobacterium in 2008. This is an interesting molecule. You can see from this data, it's a very selective anti-cancer agent. You can see now this is the activity of I'm comparing the activity of largazole with that of several other anti-cancer agents which I use. You can see largazole on this cancer cell line, activity 7.7 nanomolar, that's the GI50, whereas this is a corresponding non-cancer cell line, and then the GI50 is 122. You lower the value, more activity. Same with this cancer cell line, 55 nanomolar, and the corresponding non-cancer cell line is 480 nanomolar. So it's again more active on the cancer cell line. If you compare that with paclitaxel, actinomycin D, doxorubicin, you can see there are similar levels of activity. In fact, some of them are more active on normal cell line than on cancer cell line. So it's an interesting molecule. We want to see whether we could make analogs of this molecule and make more selective anti-cancer agents and also more potent anti-cancer agents. So this is the largazole molecule again. Now this is really a prodrug because this is a thioester. It gets hydrolyzed by esterases and it exposes the thiol group, which is a zinc binding group. And this is the linker, and this deoxypeptide ring is the cap group, which bind to the hydrophobic ring of the active site. So this shows the binding of the salt molecule to HDAC8. This is the zinc binding group, the cap group, and the zinc group. So these are some of the analogs that we designed. We decided, remember now, we want to change the cap group of the molecule, and based on the previous SCR studies, we wanted to change this part of the molecule. Now this is a thiazole group, this is a thiazole, and we want to change this part and put a polyether group there. That changes the hydrophobicity, it makes more hydrophilic. It removes some of the hydrophobicity of the molecule. Then previous studies have shown that if we replace the thiazole group with a pyridine ring, it becomes more active. So we want to see what happens if we put a pyridine ring here and here. And also the previous studies have shown that if you make this a thiazole, if you just go from sp3 to sp2, it becomes less active. But here we have sp2 carbon. So we want to see what happens with this molecule. And then in this molecule, we retain the sp3 nature of this carbon atom, but we change this nitrogen from sp2 to sp3. And we have a methyl group. Now, when you do this, you lose some of the hydrophobicity of the molecule, but we have a nice handle here. We have a methyl group which can be chemically modified to introduce more hydrophobicity in this area if necessary. So I want to show you being a synthetic medicine chemist, I have to show you some synthesis. So I'm not going to show you the synthesis of all the molecules, I just want to show you the synthesis of one analog. We use a general synthetic approach. Now this molecule can be synthesized by the cyclization of this acyclic intermediate, and which can be generated from these intermediates. Now of course this part of the molecule is common for all the analogs, only difference is in this the ring system here. Okay, so I'm going to first show you how we synthesize the side chain, which is common to all the analogs, and then I'm going to show you how to synthesize this part of the molecule, and then how we assemble the various parts and got the final molecule. Now by the way, I want to show you now, this is the molecule we are going to synthesize, because this turned out to be the most active molecule. I'm going to show you the biological activity of the compound later on. Okay, so this is how we made the side chain. Michael addition of this thiol to acetylene gave us this aldehyde, and which was then subjected to a British reaction to get this nitrile derivative as an ENZL. Oh my God. Okay, which was then isomerized to the E isomer by human passive silica gel. We got this isomer, and then we subjected that to the aldol reaction, stereocyclic aldol reaction to get this alcohol. Very quickly, I'm running out of time. Now I'm going to show you how we synthesize this part of the molecule, and that is this residue. And we started with this domopyridine, still a reaction, gave us this bipyridine analog, and the methyl group was oxidized to carboxylic acid, and then it was esterified to get the methyl ester, and then we introduced a silane group at this position with the palladium catalyzed coupling reaction, and then the silane was reduced to amine by catalytic hydrogenation. And then we made this, now we have already made this, we did the acid transfer to get this intermediate, which was then esterified with valine by Yamaguchi esterification to get this intermediate, and all we had to do now is to remove the methyl ester group and the FMOC group and cyclize. So we did this by first treating with lithium hydroxide to remove the methyl ester, and then FMOC was removed with diethylamine, and finally cyclize to use this intermediate. So one of the problems with this synthesis is this is a bottleneck, because the hydrolysis of the methyl ester with the lithium hydroxide was difficult, because there are two ester groups. There is another ester group here, though it's more sterically hindered, it is still vulnerable to hydrolysis. So we got a mixture of product, and therefore, so we improved the synthesis. We went back, instead of a methyl ester, we introduced a ethyl ester group here, and at this stage now we could remove both these groups with ammonium chloride. Then we got both TMS and the FMOC group are vulnerable. We can be both simultaneously remove the TBAP, and then we cyclize the product. So as I'm running out of time, I'm going to very quickly show you. So these are various analogs we made. I want to show you the biological results. We send these samples to the NCI to be tested in their 60 cell line assay. You cannot see these numbers. You probably will have to trust me. Now this is the growth percent of the cell line. These are the 60 cell lines. Now this is the mean value. For this molecule, the mean value is 30%. That means it's about 70% inhibition. And for this molecule, it's about 40%. That means it's 60% inhibition. And whereas for this molecule, it's minus 18. It's more than 100% inhibition of the cell lines. So it is. I have 1 minute more. And just to compare the activities of these different molecules, you can see these molecule this largazole and this our molecule J2. You can see it's much more active on this particular cell line. And this is the case in most of the other cell lines too. It's more active than most of the other cell lines compared to largazole. I'm going to skip the molecular modeling and just show you one other slide. This is the most important one, I think. Now this shows the activity of a molecule on different HDAC isoforms. This is activity on HDAC 1, 2, 3. Remember this HDAC 1, 2, 3 belongs to class 1 and HDAC 6 belongs to class 2. And you can see, if you compare largazole, the activity of, if you compare the activity of HDAC, largazole and HDAC class 1 versus HDAC 6, which is class 2, the difference is about 20-fold more active on class 1 compared to HDAC 6, which is class 2. Whereas if you have a molecule J2, it is about 440 times, 440-fold more active on class 1 compared to HDAC 6, which is class 2. And that. Okay, just one more slide. So this is the flow chart. This is how the NCI test compound. When you set a compound, they screen the compound at single dose at 10 micromolar. If it's active, they do a dose response. If it is active, then repeat the dose response. And if it is still active, then they ask for more compound, they do active toxicity testing. And so our compound has reached this stage. We set the compound, it was tested on in vivo in animals, it was well tolerated at 50 milligrams per kilogram level. So now they want more compound to do what's called the photobiography and then the xenograft. So it's really promising molecule. We are excited about this. And finally, conclusion, we have made these molecules, and J2 is more selective than largazole for class 1 HDAC compared to class 2. But I have to show this slide because this work was done not by me but by the students. This was started by Dr. Praveen Bansali, who is now a postdoc at Johns Hopkins. He started the project. He made some analogs which I will talk about today. And then it was taken over by Dr. Jihad Alman, who is in the audience here, who just returned and joined the University of Jordan College of Pharmacy. Now he synthesized most of the analogs that I talked about today, including J2, which is the most active analog. And then I had Mohashi, who is a current graduate student, who is still working on this project. He made a few analogs too. And also my collaborator, Dr. Robert Cassie from Johns Hopkins School of Medicine, and Mary Clark from Penn State University, who did the isoform testing, and students, and financial support from the DRC Memorial Fund and HCED Iraq, and provided financial support for IDAR. Thank you very much.
Well, thank you, Professor Tilkirat. Any questions, please?
Yeah. Thank you for this presentation. I thought these structures very interesting as they look at a macrocyclotactile. Have you ever thought testing these as antiviral or antibacterial?
We have not tested. That's something that's been very good. Because some of these anti-cancer agents are antibacterial also. They turn out we haven't tested So our focus is currently on anti-cancer. We are trying to get, now we want, the NCI wants 65 hectares immediately to the by the rest we are in investment. And once it is done, we have to make another 2-3 grants for the single testing. So we will try to build that and we will try to test on our country. And also, each tax, I didn't have time to talk about it. They act not only on discourse, they also have based on discourse proteins like P53 and so on, each of protein. So they have other disease effects. They can have inflammation, neuroprotection, and so on. There are other drugs which are doing this.
So I just want to add one point. Usually we have a very cytotoxic, strongly cytotoxic compound at lower concentrations. For example, this compound has anti-cancer activity. We usually don't try to develop antibacterial antiviral. It's already killing cells, so you don't want to take antibacterial antiviral and strong cytotoxic activity. So that's a good point, but if you look at the other side, compounds are cytotoxic, so they really can be developed for the clinical picture as antibacterial antiviral because of their cytotoxic.
But incrementally, neuroprotective, those are properties that have been reported to its definition. So those are things that we want to do.
Well, thank you, Prof. That's okay.
The toxic study that I reported is done by the NCI. Now they don't go to positive certification of the qualified vaccine. And it is active in the drug. So we have to make more compound. That's about it. So it's a long thing that it takes time to make this compound.
Thank you, Professor. Our next presenter is Dr. Faris Abachi. His PhD is in pharmaceutical chemistry in 1992. He has more than 250 papers published. He has 6 patents also, and he supervised 13 master's students, 6 PhD students. He's on the editorial board of many journals, and he attended more than 60 conferences and has many membership in many scientific organizations. And the title of his presentation is, it's not on the screen yet. Let me see here. Design and synthesis of some new derivatives of nitric oxide buildings. Dr.
Thank you very
Faris.
much, all
Design and synthesis of some new derivatives of nitric oxide buildings. Production came on the book. And acknowledgements. Production. Well, nitric oxide play an important role in pharmacological and physiological action. Most organic nitrates can play an important role in this. Active molecules. The best and old example would be nitroglycerin, used as substitute. The new research area for the nitric oxide donor candidate as ecology, pharmacology, and would be anti-inflammatory, antimicrobials, and gas storage. So the NO came from many sources. The famous one will be nanoid, and other types may be from sodium nitroprusside molecules, amine nitrate, nitroglycerin, or glycerin, trinitrate, and other di or trinitrate derivatives. The nucleus may be furan and other ketone elements. If we take a review for this nitric oxide, more than 30 years ago, nitric oxide can play as pollutant gas. Nowadays, there are 3 gas messengers. The first one messenger will be nitric oxide. The second messenger will be sulfhydrated group H2S, and the third one, the carbon monoxide. This is the chemical structure, simple molecular structure for the N gas or nitric oxide, but the proposed mechanism, it's well known from all arginine will be nitric oxide synthesis, dehydrolysis to gives an L-citrulline, and the active ingredient, active product will be nitric oxide. There are many sources here for the nitric oxide is either free radicals or cleavage of the molecules. Types of nitric oxide, as I mentioned in the second slide, will be from organic nitrate, nitrites, sodium nitroprusside, and/or donors, nitric oxide, ventilation, and miscellaneous types. So now the most area focus for the non-steroidal anti-inflammatory drugs, anti-angina, anti-cancer, and other types. A. The aim of this work will be synthesize 3 series of nitric oxide. Yes, series 1 will be nitric oxide for the heterocyclic atoms or agents by condensation of haloalkyl alcohols with acids, different mineral acids. Series 2, the docking design and docking for the series 2 will be for the nitric amino acid derivatives for the di and other types of peptide using DCC. And the third series is the difficult series, will be using cyclic ether, will be nitroxyl alcohols were synthesized directly condensation epoxide with the sodium nitrate. Experimental parts, either synthesis, identifications using many spectroscopic data, FTIR, NMR, UV, GC mass. Theoretical calculation for the docking will be taken via ab initio and molecular mechanisms calculation theoretically using advanced chemistry developed special programs ACD V11, version 11, 2009. Software using a best computer and large memory. The initial doses can be for the molecule can be used for the stereochemistry 3-dimensional molecule employed to determine the equilibrium geometry for the molecules. The docking takes place will be taking auto-docking. There are many techniques we use or select auto-docking for the most sophisticated software research community.